Hi everyone, welcome again to the course of structural biology. We are going through structural biology techniques. We have discussed high resolution technique like X-ray crystallography, NMR, we have discussed spectroscopy. Currently, we are on the module of cryo electron microscopy. We in the first class of the module we have discussed about the general principle of microscopy, electron microscopy. Then in the second class we talked about the general procedures and details of cryo-electron microscopy. Today we will discuss about data collection and data analysis, which are core part of this technique. So, cryo electron microscopy, data collection and analysis. If you remember, in the last class I have discussed about the total procedure. We talked about sample, how to prepare the sample, how to take care of the sample, then going for negative strain visualization, and then coming to cryo EM visualization, grid optimization, and after that, after grid optimization, you have to come to cryo EM data collection and then cryo EM reconstruction on superior microscopes, and the procedure will go well when the sample appears reasonably homogeneous. If also you could see the sample directly under cryo EM visualization, escaping the negative strain visualization step. From negative strain visualization you could go to negative strain reconstruction and then come to cryo EM visualization. If the sample aggregated or heterogeneous or not well distributed on the grid, or you need optimization of staining or sample, then you have to stop here and again go to sample preparation. So, grid optimization, up to that this is your checkpoints. From cryo EM data collection you could do single particle reconstruction, and then from cryo EM reconstruction you could go to single particle reconstruction. So, today as I told, we will talk about cryo EM data collection, and there are many factors which influence the cryo EM data collection: imaging condition, microscope alignment, image acquisition, data quantity, image digitization, a lot of things. So, let us know about them, what are the procedures and how they influence the total process. So, once the protein density and ice thickness or quality have been optimized, what is that? We talked about that, the protein making it homogeneous, and the ice, they should be transparent ice, which is called the process of vitrification, and initial data collection should be performed on a mid range electron microscope. What are the range and all we will talk about. The goal is to obtain 2D reference free class averages which have high resolution features at the level of secondary structures like alpha helices, or like where there are stable structures. Particles should be hand picked at least at first to avoid the problem of template matching and Einstein form noise, which is a criteria Einstein overfitting we used to say. With modern field emission microscopes and direct detectors, only a few hundred particle images are needed to generate a 2D class of sufficient resolution to see the alpha helices. Only few hundred with the modern field emission microscope and definitely with the direct detectors. Thus, a data set of a few thousand particles should be sufficient to yield a few high resolution classes. If high resolution 2D classes are not obtained, the specimen should be re-evaluated and optimized, including modification of protein preparation, buffer, detergents and surface modification and the addition of support films like amorphous carbon or graphene. So, basically if you come to that stage and you do not get the high resolution 2D classes, you have to re-evaluate the entire thing, you have to optimize again and come back. Particles that do not align well may be partially or fully denatured and could lead to incorrect structures if the subsequent computation and validation is not done with great care. So, you have to see that while the processing of the sample, the protein would not be getting denatured or partially fold or something. Many high resolution structure to date have relied on discarding a large portion of the particle from the initial data collected. If you think that the data collected from the part of the protein which is denatured or not good, you should go and discard. The proportion of discarded or junk particle can vary by orders of magnitude from one specimen to the next, depending on the specimen nature, its stability, its preparation and all many factors. So, experts suggest that if not most of these particles are damaged during the sample preparation process, you could go for rejection. By evaluating specimen preparation using the above criteria we talked about, one can optimize the specimen and improve the particle yield. So, you come there, you evaluate, you are not happy, go back, optimize, come back, you definitely improve the particle yield. This is generally preferable to collecting large data sets and discarding most particles to reach a desired resolution. So, you collect more and then you have opportunity to discard. Improving particle yield will make the entire process more efficient and more likely to succeed towards the data analysis. Once a preliminary data set is collected that generates suitable 2D classes, a larger data set with a few hundred micrographs and several tens of thousands of particles is collected on the mid range or high end microscope, from which an initial 3D map can be calculated. There are several important factors that to be evaluated. First of all, do the 2D classes show several distinct views of a particle with self consistent dimensions, each with secondary structural features. Second, is the orientation distribution sufficient to allow calculation of a 3D structure with isotropic resolution? Those fundamental questions about orientation, dimension and all we have to take care. If the orientation distribution is not suitable, one can alter buffers, add detergents, change the plasma conditions or use alternative surface. Those are the availability of options we have. Generally, people use graphene or amorphous carbon to improve the distribution and promote additional views of the complex. Cross-linking, which we talked about in the previous class, can also alter particle orientation, since modification of charged surface amino acid, most often it is applied to lysine, changes the surface properties of the molecule and their interaction with the supporting surface and the air water interface. Collecting small data sets will be sufficient to determine if any changes in preparation conditions were effective at improving the orientation distribution. So, when we see that we have to check and go back, we should collect small data sets, not spending more time on initial data collection. If the resolution of the initial 3D reconstruction reaches a reasonable resolution for the number of particles and image acquisition settings, a larger data collection on a high end electron microscope should be performed with the aim of obtaining a high resolution structure. So, again the thing we are repeatedly talking about, the initial data collection, when you are not sure about, you do it with a low resolution microscope, take minimum amount, then evaluate, and when you reach to the idea that you have good sample, then go for high end microscope, then go for collection of larger data set and all. What constitutes a reasonable resolution will be arbitrary and should ultimately depend on the resolution of the biological question and the state of the technology, but as a guidance, experts recommend sub nanometer resolution should be routinely possible from 10 to 50,000 asymmetric particle image. So, this is always a good questions in terms of when you are considering the possibility of optimizing. You will say what is the resolution, what is a good resolution, what resolution is a good resolution. The answer is good question, which means the perfect answer is not available. It is dependent on the question you are asking, it is dependent on the setup you are working and many other things. A compromise is always required. With this in mind, a large data set 500 to 1000 micrograph and 24-hour of microscope time should be collected with the best available microscope. In this study, we are talking about a 300 kilovolt instrument with commercially available direct electron detector or DEDs. The data collection strategy will depend on the size of the particle, the resolution desired and the particular microscope available to the microscopist. So, basically one, the biological assembly. What is the size and what is the stability? Talked about size, stability. So, that is the first thing. Second, the resolution you want. So, resolution required or targeted. So, this is A, this is B. Then the C is definitely the microscope setup, means the microscope available. So, three factors: biological assembly in terms of size and stability, resolution required or targeted, and microscope setup. All biomolecular complexes exist in multiple conformational states, and for each to be resolved, even more high quality data required. So, as we are getting opportunity to work with the native sample in its aqueous state, you could say that you are going to get the biological sample in different conformation, and more diverse it is, more high quality data is required. Many computational algorithms are available to help extract this information from a data set. So, you have the data set, your algorithm will work and extract the information regarding the multiple conformation. In some case, ligands, those are small molecule binding partners, nucleotides, cofactors can be added to stabilize particular conformation or to interrogate a particular biological question related to how a ligand affect the conformational state of the complex. So, there are different things. One, you have three conformations and then you want to popularize A, and you know that that would happen by binding this. So, you use that ligand, you popularize A and lesser the conformation, easier to get high resolution data. That is one. Second one is a different problem where you have the protein, you get the structure already. Now, you want to know the alteration when you add a ligand or a binding partner. So, these things are possible through these techniques. This usually require the collection of additional large data sets to achieve high resolution after small data sets have been collected to confirm the change in conformation or presence of the ligand of interest. Finally, most importantly, all high resolution data sets should be collected with validation in mind. In particular, experts recommend is to collect a small set of tilt pair 1 to 2% of the number of micrographs with every data set intended for determination of a previously unknown structure. They can be subsequently used to validate the reconstructed density map. We have given a lot of examples so that the interested reader should go through their literatures. So, you have this density map and you have to validate the reconstructed density map, measure the angular accuracy of the projection assignment, because I will talk about in data analysis when you have 3D to 2D to again 3D, you get the projection and determine the absolute hand of the structure. By using the systematic approach described here, the microscopist will have the best chance of efficiently going from a protein in solution to a high resolution structure. So, I talked about the whole thing, but here I am explaining the case by talking about the steps, what are the steps taken, the representative data, how the data would be evaluated and type of cryo-electron microscopy used. So, first it is sample preparation. You see the SDS gel, the sodium dodecyl sulfate gel, these polyacrylamide gels, they help getting the molecular weight of the complex, and then we do different spectrophotometric studies to determine the presence of protein, protein's concentration. Here the evaluation criteria would be the composition in the mixer, the purity if single protein or anything are used, the stability where the complex type, buffer composition, and then the biochemical activity. After the protein sample is prepared with homogeneity and considerable amount of purity showing the biochemical activity, in the second step we are having negative stain. So, you see how the particles look in the negative stain. Here we need to see the discrete particle. If you see, you will see the presence of the discrete particle. Again we will evaluate the stability, we will measure the particle size and shape. The microscope required to measure those things are actually a very basic entry level transmission, cryo transmission electron microscope. Then going for cryo-EM visualization, you also call it diagnostic cryo-EM. Here you are going to look for stability, particle size and shape, particle distribution versus concentration. You need entry level mid range cryo-electron microscope for that. Then initial cryo-EM data collection, you see the particles, the distribution. You need high resolution 2D class, initial 3D model have to be developed from that. You have to get the orientation distribution and you have to measure the particle yield. To do that, you need mid range high end microscope, and then high resolution cryo-EM data collection, which is giving you the molecular level representation. Here you see the structure of the ribosome, which is a favorite thing for the cryo-electron microscopist to work on that. Here you have to work on the tiltation, the tilt pair to and validation, because here you are identifying the different conformations, the motion statistics, the angular accuracy, the local overall resolution and conformational state, and for that you need high end microscope. So, as with most technological devices, there is a trade off always between the ultimate performance of the current microscope and the other requirements, like the type of detectors, the amount of money and the effort required to achieve the performance. But since the goal is ultimately to determine structures at resolutions which are sufficient to unambiguously answer the biological questions, the compromises should be reasonable. There should always be a balance, so that we could get the biological information we are looking for at a high confidence level. Between the performance of the instrument and the amount and quality of data required to achieve a particular resolution that is appropriate for the stage of structure determination. So, trade offs are still there. In general, we think it is better to spend more effort on preparing optimal specimens, that is, we should put more time on sample preparation, as now and even more so in the future. This is where the biggest difference in the resolution and interpretability of the resulting density maps are likely to come from. If your protein sample is homogeneous, is stable, you always have a advantage. Since biological imaging is ultimately limited by damage to the specimen, currently the most important single factor governing the quality of the micrograph is the efficiency of the electron detector. Using the current understanding of detective quantum efficiency, or DQE, and published measurement of DQE for the various commercially available detectors. This, in conjunction with the illumination and specimen movement consideration from the basis of experts recommend imaging condition, which we are talking in the next slide. We have developed a table. This can be considered a starting point for the users to make trade offs in the amount of data collected versus resolution or other factors like microscope time, and they will certainly change as the technology continues to develop in the coming years. As you see, we have understood the basic physics principles to improve this. It is ensured that in coming years a lot of more improvements would be possible. Also, here I am trying to show a standard protocol for data collection at high resolution on a cryos with a Falcon 2 detector. The protocol is easily adapted to other specimens. So, we are making it targeted specific protocol, but it could be easily adapted to other specimen and microscope configurations using the data collection settings we are going to discuss in the tables. So, one, the general classes of cryo transmission electron microscopes. We are talking about them entry level, mid range level, upper mid range level and high end. So, entry level, a typical example is FEI T12 Geol 1400, and the marginal cost by day in 2016 is €250. So, for the entry level, because you have to consider the cost also. In the mid range FEI F20 Talos Geol 2100F, the cost per day is €600. Upper mid range, the cost is 1000 per day, €1000, and for high end FE Titan Cryos, for what we are talk about the next protocol, €3000 per day. Specimen support geometries for particular applications. For negative stain, you need 400 mesh grid, you do not need the foil, and the film 50 to 100 angstrom, and there are different modes as we have discussed in the figure before. Negative stain diagnostic cryo, medium resolution which is around 3.5 angstrom cryo, high resolution higher than 3.5 angstrom greater than 400 kilodalton substances, higher resolution less than 400 kilodalton substances, very high resolution cryotomography and cryotomography with high resolution subtomograph averaging. You have to have the grid, foil and film according to that. Also the detectors, there are different detector types like phospho-CCD, phosphor-CMOS, direct integrating and direct counting, which are specific for cryo electron microscopy, which kind of have taken a very big role, very important role in the improvement of resolution in the electron microscopy. So, coming to the protocol for high resolution data collection, you have to load the specimen in cartridge and mount in auto loader, including a calibration grid which could be graphitized carbon or similar material. Discard any that are bent or broken during handling. Load a specimen in the column and use low magnification to check grid is intact and contains several squares with an appropriate thickness of ice. So, again the vitrification, ice thickness is best judged at low magnification by increasing the defocus to hundreds of micrometer to improve the contrast. Once a grid is selected for imaging, load the calibration grid and perform standard microscope alignment in low dose exposure mode. On a well aligned and stable cryos, these include gun alignment, condenser and objective aperture alignment, beam tilt, coma free alignment, camera gain correction, condenser and objective stigmation. We have discussed about set up the exposure mode using the parameters we have in the table. Reload the selected specimen and locate all the squares for data collection using low magnification and high defocus. Using automated software to create a montage of images at low magnification can be useful for that purpose. All squares for data collection should be free from cracks, crystalline ice and contamination. Collect a couple of test micrographs to confirm ice phase, thickness and particle distribution. Set focus in exposure mode using beam tilt or by looking at the fringes or bright spot at the edge of the hole. This is a research work who have seen the changes. Check the illumination geometry of the beam in exposure mode. It should be round, centered on the imaging axis and centered on the hole while encompassing an annulus of the support around the hole, which is explained in our next figure why it is important. You begin the data collection either manually or using automated data collection software. Check the focus and illumination every 20 to 30 holes. If mounted correctly, focus should be vary to less than 1 to 2 micrometer across an 80 micrometer square. That would be the checking criteria. Collect a few 1 to 2% of the total micrograph, tilt pair micrograph for validation, tilt angles and exposures of 0, 15 degree and 1-3 second respectively are generally reasonable for validation. So, we talked about the focusing. So, it is testing for specimen movement during or after data collection. So, large amount of specimen movement or stage drift it is called can be detected during data acquisition using real time first Fourier transform FFTs of the collected micrographs. FFTs of specimen are shown with no stage drift here and 10 angstrom per second temperature induced stage drift. So, here no stage drift is observed and here 10 angstrom per second temperature induced. This micrograph, the C shows the recommended symmetric illumination of a frozen specimen suspended across a hole in an all gold support foil. Histogram is the in plane movement statistics for 1 second micrograph on all gold support versus amorphous carbon on gold under the same symmetric illumination condition, which is shown here. This is the enlargement of the histogram near origin to get a better look. Now, every data set collected using a direct electron detector should be checked to verify that the specimen preparation and illumination conditions are optimized to minimize the particle motion. Currently, the simplest way to do this is using a per micrograph motion correction program like Motion Core. Each micrograph is collected as a movie where the total dose is subdivided into individual frames. The algorithm is used to determine the overall movement of the specimen in the micrograph with time and then offset the resum the frames, thus removing some of the information loss. The program is fast as it is implemented for a GPU architecture and therefore can be used to quickly check the overall movement of the specimen support during imaging. Distribution of movement for micrographs in a 1 second exposure, which as we talked before in a Titan Cryos on Falcon 2 direct electron detector with 1.7 angstrom pixels. Both the sets would be collected with recommended symmetric conditions. On all gold support, the movement is less than 1.5 angstrom, which is less than 1 pixel in the image. So, you could bear with. On standard quantifoil support under the same condition, the per microgram movement is an order of magnitude larger than this. Thus, with ultra stable support and modern low drift microscope stages, if you use micrograph motion tracking algorithms to check for incorrect data collection settings, stage drift or damage to the foil or grid, since under normal conditions with ultra stable supports, the overall movement of the specimen support should be essentially undetectable. Coming to the next stage, the data processing. The image processing pipeline in single particle cryo EM is required to solve the 3D electron density of a target molecule in potentially many conformational states from noisy 2D images collected using the cryo TM. Each collected image is a movie of dose fractionated frames that require motion estimation and correction. We talked in the previous section also. The corrected images are then used to estimate the microscope CTF during the exposure as well as to find and pick out the single particles. The single particles are extracted from the micrographs and then are sorted and filtered using 2D classification method. So, you have to look at the different particle in different orientation and then separate them or classify them. The resulting filtered particle stacks are used to perform ab initio 3D structure determination of potentially multiple discrete states or targets. These core structures are then further classified and refined in 3D to yield interpretable molecular density maps and achieve state of the art resolution. Each of the processing stages above can have parameters and inputs that require decision made by the scientists using structural and other insight as prior knowledge to guide the processing. If you have prior information, it is always very useful for the data processing. Typical workflows on difficult molecules often involve multiple iteration of segment of the processing pipeline. So, you do the same thing multiple time towards going from a initial model to refined corrected model. each time with changes in the selection of input data or parameters to yield the optimal results. In particular, curating data and separating a sample in silico into multiple homogeneous subsets representing different conformations can require knowledge both of the target and the underlying algorithm. Coming to single particle analysis from the data to construction of the single particle. This is perhaps the most commonly used variant of cryo electron microscopy, the single particle analysis. In this technique, data from a large number of 2D projection images featuring identical copies of a protein complex in different orientation are combined to generate a 3D reconstruction of the structure. When atomic models are available for some or all of the subcomponent of the complex, they can be placed or fitted into the density map to provide pseudo atomic models, considerably extending the information obtained by the electron microscopy. So, isolated macromolecular complexes randomly oriented in solution can be trapped in different reaction states by vitrification, no crystallization or ordered assembly needed. The position and orientation of each particle must be determined for 3D reconstruction. So, the macromolecular complex, they would be randomly oriented, means they would be staying in multiple conformations, but they could be trapped in different reaction states. So, let us say if you say shape wise, so you get this and then you get this, then you get this, you get this, you get this, you get this, like this. No crystallization or ordered assembly is needed, which is a big advantage as we typically talk in X-ray crystallography. The position and orientation of each particle must be determined for 3D reconstruction. The more particle used, the higher the resolution. So, for those isolated macromolecular complexes, mixed states can be separated. So, you get the different states and you then separate them. So, this is a kind of purification using computer, because you get different alignment and then you separate them, classify them. Ultimate limit to resolution from radiation damage, interpretation by atomic structure, docking or direct determination of the backbone is possible. So, let us start thinking about a single particle. All the cows there roaming here, considering cows as single particle, we consider them as single particle. Then we collect data, the data is signal to noise is low. As you see, you could not see anything, but then you process, you get these images, the low resolution images, and then you have the initial rough 3D model. Rough, if you compare, you will see the cow had some other color which you do not get here because low resolution model. But with this rough model, you identify differently oriented conformers. So, now you get the raw images, you align and group them into classes and you get 2D class averages. Now, from the 2D class average you reconstruct and you get the new 3D model. The new 3D model is much better image than the initial rough model. That is where the image processing. Also, you have to find the orientations. If you see, you have the carbon base, you have the vitrified ice, and the particles are in different orientation. You need the parameters to determine those orientation. This would be the key here. Also, if you see, you average similar views, you improve the signal. So, this is the individual raw images. You could see something here, but they are under very low resolution. Now, if you average, let us say you make a sum of 4 to average them, you get picture like that. A better picture with sum of 8. So, you get more sample, you get better, and then it is much better because sum of 32. So, more you take, more you do average, better signal to noise you get. So, from this scenario to this scenario to this scenario, C is better than B is better than A. So, if you come to a summary, what we perform for single particle image processing, we get the data, then we identify single conformations or orientations and we pick them up, that is called particle picking. Then when we separate them, we make the classification, and once we do the classification, we do the averaging. Averaging gives better picture, then we align with them. That is the single particle image processing summary. Coming to the 3D reconstruction. The goal of 3D reconstruction in cryo electron microscopy is to take 2D projection and turn it into its 3D volume. This allows for the visualization of small structures within the sample. It is essential to reconstruct the 2D projection because the information gained from the projection itself is limited. So, the projection you get towards 3D is limited. So, you need to reconstruct it. So, this is what we perform. A projection occurs when a 3D image is taken and those points are then put onto a 2D plane. So, we take a 3D object and then the points are put into the 2D plane. Now, what happened? Each point in the 2D plane corresponds to the slice in the 3D volume and is based on Radon's theorem. It is possible to obtain a 3D volume, get the 2D projection, subsequently take the Fourier transform of the projection and use the Fourier transform of the projection to obtain a slice of the 3D volume. So, here there is a volume, you only get the points in 2D. So, 3D object, you start with the condition A, you come here and taking the 2D projection, you do 2D Fourier transform, you get a 2D FT, and then you get a 3D fit of object which is giving you a slice, and now you do 3D inverse. Thereafter, it is possible to take the inverse Fourier transform of the slice yielding the same volume. So, this is C, this is D and D goes to A. Before proceeding to reconstruction, it is necessary to know in which direction the particles are facing. The orientation of the particle can be determined using the Euler angles. Now, the Euler angle can be defined in two ways. According to first definition, the orientation can be determined by using the latitude, longitude and rotation in plane of the particle. The second definition takes into the z and x axis. The initial position is determined using the z axis. Next, the particle is rotated and the orientation is derived from the new x axis. The third and the final calculation is based on the location of the new z axis after it has been rotated around its x axis. So, a back projection, we have to know about back projection. The back projection is basically the inverse of the radon transformation we talk about. It is the process where a 2D projection goes into a 3D model. It is the only method that can be used for this purpose. A back projection reconstruct an image by taking each view and smearing it along the same path it was required. So, you could see how the rotations happen in the Euler angle. The result from this is a blurry version of the correct image. So, what are the 3D reconstruction process steps? 3D reconstruction process estimate the unknown orientation and 3D structure at the same time. The 3D electron density maps are created from the 2D projection as we discussed. The angle of projection relative to each other are first determined, then find a common line of projection to determine the relative angles. You have to do the observation of the specimen, the contrast of the specimen depend on specimen itself, defocus value of the objective lens and thickness of the eyes. There are three methods of observing and recording images: fluorescent screen we talked about, photographic film we talked about, CCD cameras and just as an extension the DED setup. So, 3D images of biological sample is obtained by the process called cryo electron tomography or CET, where a 3D reconstruction of the sample is created from the tilted 2D images. Because of the tiltation we get the angular changes. The raw images from different projections are recorded and at last they are stitched together to form the required 3D structure using the computer software. So, if you see, this is the object and first, second, third those projections are taken. 3D reconstruction process estimates the unknown orientation and the 3D structure at the same time. The 3D electron density maps are created from the 2D projection and angle of projections relative to each others are determined and the find common line projection to determine the relative angles. So, reprojection, the 3D density map can be used to generate the projection that can be used to realign the raw images. The process may have to be repeated for different time. Then there would be automated particle picking, identify the particles in the micrograph and cut out patches containing the one particle each, like here if you see we have to find out these ones in that way. This can be done automatically because the manual process is tedious and difficult. Then we have image enhancement. Image noise is the random variation of brightness or color. Information in images produced by the sensor. The cryo EM images are very noisy and have very low contrast. So, here you do the enhancement and you get the better picture. Smooth the noise as well as enhance the contrast. In summary, the cryo EM is a form of transmission electron microscopy where the sample is studied in its native state at cryogenic temperatures, used for 3D visualization of biological macromolecules. The resolution of cryo EM is not high enough as we have seen here, but it is improving using different computer techniques and many other additions. With the advancement of technology, this technique will certainly improve and the effect have already started to be observed. In the next class, we will talk about the story of how the advancement of cryo-electron microscopy happened from 1970s, started at the initial stage, how the one after other innovation have contributed towards high resolution starting around 100s to 50s angstroms resolution. Now they are regularly attending lower than 3 angstrom. So, we will talk about the resolution revolution, we talk about the journey, and we will talk about the future and some of the modern innovation, recent innovation help the resolution revolution. Thank you very much for listening.